Let me begin by thanking the organizers for inviting me here. It's a great honor, and for the excellent hospitality which all of us have been enjoying. So the topic today is atoms of space-time, probably more precisely atoms of space. I will use that a bit loosely, and its connection with the nature of gravity. Most of what I'm going to talk about you will find in this review, which I have written recently. I will begin by what many of us who work in this area consider to be a self-evident truth. Namely that there is, if you stare at classical gravity carefully and correctly, it will tell you that its equations in a large class of gravitational theories, including but not limited to Einstein's gravity, it has the same conceptual status as the equations governing elasticity or hydrodynamics. Those of you who have not been working in this area or reading these papers, it wouldn't be self-evident at all, but don't worry, I'm going to make it self-evident as we go along. What I'm going to do today is to ask the question, why? How can we understand this peculiar affinity of gravity to behave like the thermodynamic limit of an underlying statistical mechanical system, both microscopically and macroscopically? Now, this why needs to be understood. For example, if somebody tells you that two bodies of different mass will fall with the same acceleration in a gravitational field, you can ask why. And he will tell you that is because the gravitational force is proportional to the inertial mass. So shut up and don't ask any further. And that will explain everything. But we know that that is not a good answer to that why. The good answer is provided by understanding that gravity is described by a curved space-time, and particles move in geodesics. Geodesics in a given metric don't care what the mass of the particle is. That is why particles move with the same acceleration in a gravitational field. In the same sort of way, this affinity between thermodynamics and gravity can be understood loosely by just doing some kind of a quantum field theory in curved space-time and stuff like that. But I'm looking for a deeper layer of answer. And in fact, I will convince you that there is a deeper reason, and this reason is a bit surprising. If your gravitational theory has to be immune to the zero level of energy, that is, if you shift the zero level of the energy, gravity should just ignore it. If gravity has to be defined and developed, taking this guiding principle into account, then it must have a thermodynamic interpretation. This connects two concepts which are usually thought to be completely separate. The zero level shifting is usually talked about in the context of cosmological constant, etc., etc. And the thermodynamics is usually talked about in the context of black holes, Redler horizons, etc. But I'm going to tell you that there is a way of connecting these two things up. So once we do that, you will find, this is a kind of a rapid summary of what you are going to hear. You'll find that the field equations of gravity can actually be obtained by maximizing a heat density of gravity plus matter on null surfaces. And null surfaces will play a crucial role all along. And in fact, for those of us who have forgotten our thermodynamics 101, just to remind us, what characterizes the more being different is the existence of something called heat, which is temperature times the entropy, and per unit volume, it is the temperature times the entropy density, which I will call heat density throughout. And this heat density, if you take for matter and gravity and add it, and then you maximize it for all the null surfaces simultaneously, the resulting equations are equivalent to the gravitational field equation. It works for a very wide class of gravitational theories, and the entropy density determines which theory you are choosing. And of course, it also works for Einstein's theory. The time evolution of the space-time can be interpreted in terms of some suitably defined surface and bulk degrees of freedom in a region, and the difference between them drives the time evolution. And in static geometries, these two numbers will be equal. And this is a very nice way of looking at the entire gravitational dynamics. This implies and is implied by Einstein's equation, for example. In this approach, gravity responds or reacts to the heat density of the universe. And for an ideal fluid, heat density is just P plus rho, and not to the energy density. And among all the ideal fluids, only P plus rho equals 0, or P is equal to minus rho, which is the cosmological constant, which does not have the heat density. So gravity ignores the cosmological constant. But it comes up in a different avatar as an integration constant, somewhat reminiscent of unimodular theories, but not exactly the same. And its value is determined by a new conserved quantity for the universe. Right toward the end of the talk, I will give you a formula which tells you the numerical value of the cosmological constant. OK, now let us go a bit further. If you want to look at it from a microscopic point of view, you would like to think in terms of a distribution function for atoms of space. And that can be connected up with this variational principle I talked about, which comes from a very strange feature that renormalized or dress spacetime endows each event with a 0 volume but finite area. I'll explain how this comes about. Now let us get on with the details of what I just summarized. In gravity, there is a sharp distinction between the kinematics and dynamics. All the elegance and gorgeous beauty of Einstein's theory comes just from kinematics. The dynamics does not have a good guiding principle. In fact, it's pretty ugly. If you don't believe me, just imagine how many people make their living with alternate theories of gravity. There are very few people who make a living with alternatives to principle of equivalence. Okay, that tells you how rigidly kinematics is structured while dynamics is still flapping around. So let me explain the kinematic part. Take a spacetime, take an arbitrary event. These are null rays going through this event. And you go to the freely falling frame at that event. In the freely falling frame, the null rays become 45-degree lines. Here is a freely falling observer. There is a region in which it is valid. And if you just say that the special relativity should hold in the freely falling frame, you already get the kinematics. And for the purpose of my talk, everything contained with the matter is described by just one energy momentum tensor and its conservation law. And that essentially gives you, once you covariantize it from special relativity, it gives you how gravity affects the rest of the matter. Now, the important consequence of this, when you add general covariance, is that there can be regions of spacetime which are inaccessible to certain class of observers in any spacetime. This has nothing to do with black holes or de Sitter universe or any such thing. You can construct them in any spacetime. And it also gives you a lesson that you need to take non-inertial frames a little bit more seriously than what differential geometers would like to tell you. It is just a coordinate relabeling. No, it is a lot more than that. If you take that seriously, you are led to what I believe is the most beautiful result which we so far have in the interface of quantum theory and gravity. It tells you that if you have an observer who perceives a horizon, he will attribute to spacetime a temperature, which is essentially proportional to an acceleration, suitably defined acceleration, which can be traded out for other geometrical quantities. This temperature has absolutely nothing to do with the field equations of gravity. This is purely kinematic. You give me a spacetime, I will give you a class of observers. If he has a horizon, I can tell you the temperature. So this doesn't have a dynamical content, but it captures the kinematic. So here is a classic example of the Unruh effect. This is a uniformly accelerated observer with horizon. He will see a temperature. There is also a very well-defined controlled approximation by which you can generate a local version of this. What you do is that you have the freely falling frame here with 45-degree line. And here is this guy who is sitting quietly. So he is accelerating with respect to the freely falling frame. And it turns out that the vacuum fluctuations of the freely falling observers will be interpreted as the thermal fluctuations by this, what I would call the local Rindler observers. This is a very non-trivial equivalence, and one can actually give a couple of talks on just this non-trivial equivalence, but I will just say it is a non-trivial equivalence and leave it at that. This introduces H cross and C. C was always there. It introduces H cross into the theory. This local Rendler horizon has two features which I want to stress because I'm going to use it very crucially. The first point is that when matter crosses this horizon, as far as the local Rendler observer is concerned, it takes a huge amount of time. It is like matter falling into a black hole, never crosses the event horizon as far as the outside observer is concerned. So the amount of heat, so because he perceives this horizon as a hot surface, you are dumping energy into a hot surface, he will perceive it as a heat, and the heat density of matter which is crossing that horizon, according as interpreted by the local Rendler observer, is just the stress tensor dotted with LA, LB, which is the normals to the null surface. There is also another peculiar feature which we will need later on. If you do a Euclidean extension of the spacetime around this local inertial frame, so to speak, the null horizon goes to the Euclidean origin. What happens here is something like this. You have this hyperbola, which is the trajectory of this Rendler observer, for example. This region goes into this circle because x square minus t square equals constant goes to x square plus t square equals constant. So as you go along this, you go round and round in this. And as you approach the origin, you are approaching the null cone. That is important. That is going to play a crucial role later on. If you take this and you sort of rotate it around, you get a hyperboloid. And you can fill this hyperboloid with hyperbolas. And when you take the limit of that acceleration going to very large values or towards the origin, what you will find is that here there is a sphere which collapses to it. So moving to the origin in the Euclidean space is equivalent to going to a null surface in the Minkowski space. OK, let me go further. So far, I have been just talking about kinematics in a given space-time. Now I want to turn to dynamics. I had already lamented the fact that we don't have a guiding principle for dynamics. I want to give you one. I claim that all other equations of motion we know for all other matter sector remain invariant if you add a constant to the Lagrangian. Gravity shouldn't go around breaking a symmetry which is present in the matter sector. So the gravitational field equations must respect this symmetry. If you add a constant to the Lagrangian, the field equation should not change. Now, adding a constant to a Lagrangian is equivalent to changing TAB to a constant times delta AB. And the field equations has to be invariant under this. Now, it is immediate. It's not even a theorem. It is probably a semi-lemma to prove that if this has to hold, you cannot vary metric as a dynamical variable in any variational principle in an unrestricted form. So I'm not going to talk about unimodular theories and things like that. So that essentially comes from the L matter times square root of minus g kind of coupling. Now, we have a bit of a problem. That is what the title implies. What we are looking for is a variational principle or an extremum principle, a local extremum principle, which should depend on the energy momentum tensor. It should depend on the metric. It should give me the equations of motion for the metric, but I am not allowed to vary the metric. So you need some other auxiliary variable. That is a bit strange, because usually if you vary something in an extremal principle, you get equations of motion for that object. But we want to vary some auxiliary variables, but get equations for GAV. Further, this has to depend on TAB, because that is how you incorporate matter. But it should still be invariant if I add TAB to this. How do I do these two? The answer to these two questions are related. What you need is a variational principle of this structure. The TAB can only appear in it in terms of dotted with a null vector field, so that if I add to TAB a constant time TAB, this term doesn't care about it. And the rest of the thing, which you have here, must depend on this NA. And this null vector field should be the minimal possibility of an auxiliary field. So I want to have a structure where you vary this with respect to null vector fields and demand that this condition should hold for all null vector fields. And that should lead to a constraint on the background metric. Only certain metrics can satisfy this. So can one find such a thing? It looks like a very strange variational principle. The answer is yes. It can be found, and it has been found quite a few years back. What you need to do is the following. The heat density for the gravity is just a quadratic in the derivatives of the null vector field multiplied by a fourth rank tensor, which has a very specific tensor structure. It is essentially a wedge product of curvature two forms, but if you write in terms of index, this is a determinant tensor multiplying this. Then one can show by just straightforward algebra that this leads to the following set of field equations. And in the field equations, you will have an arbitrary constant because that arbitrary constant is already, and shifting by an arbitrary constant does not change the invariance principle, so that is always allowed in that. These equations are known. These are called the Lankos-Lovelock model of gravity, or Lovelock model of gravity more precisely. And in d is equal to 4, that is if you're working in 4 dimensions, this uniquely reduces to general relativity with an undetermined cosmological constant. You cannot have an undetermined cosmological constant. There has to be a principle which determines its value. That we will come back later on. Now, there are several things which one can ask at this stage. To begin with, how do I interpret something like the heat density of matter? And what the heck is this null vector doing there? How do I understand that? Now, you can answer this. Having got this, you can go either to the macroscopic scales or microscopic scales. Macroscopically, you can interpret this as the heat density contributed by geometry on the null surfaces and take this Na essentially proportional to the null normal to that null surface. Microscopically, I will interpret this as a distribution function for atoms of space-time with something analogous to an internal degree, let us say, momentum, loosely speaking, Na. Okay, let us see how this comes about. First, the standard thermodynamic connection. For those of you who missed the action in this field in the last several years, microscopically, you identify this Na with the null vector, and you interpret this entire thing as a heat density. After all, this is TAB, LA, LB, I told you, is the heat density of matter. So this is the heat density for the geometry. Now, you want a more explicit demonstration, you can do it in the following way. You extremize this principle for all null surfaces, which leads to the gravitational dynamics. And you can go back and ask what this structure means. In the Lankos-Lovelock theories, once you have the field equations, you can go and construct, for example, the black hole solutions in those corresponding to those field equations. And in the Lovelock theory, this quantity determines the entropy of the horizon. So I would like to call it the entropy density, or the entropy tensor. The entropy density, what is usually called the world entropy, is essentially this quantity dotted with a binormal on the horizon. There are a lot of people who don't work in this area who believe that the entropy of the horizons are proportional to the area. That is not the case. The entropy of the horizon is proportional to its area in Einstein's theory. Concepts like entropy, temperature, thermodynamic underpinning of gravity transcends Einstein's theory tremendously. Einstein's theory is just a special case. So in general, this is what the entropy density is. It is not a constant. But if you go and look at the on-shell value of what I extremize, it will give you precisely the heat density of that theory with this complicated expression. So that tells you that what we are actually using here is the heat density. Now, up to this point, I have been talking about thermodynamics in a very loose sense. If it is genuine, then there must be something else which you should be able to do. Now, what is not often stressed or realized is that if I take a glass of water here, it looks completely continuous, but it is made of molecules or atoms. And you might think that you need to do angstrom scale experiments to discover that. Not at all. You don't need to do any experiment to understand that a glass of water is made of atoms. This is what the Austrian physicist told us. He said that if you can heat something, it must have microstructure. Because when you pump energy into it, it holds it because it has microstructure. So the mere fact that water can be heated tells you that water is made of microscopic degrees of freedom. In the same way, it in fact goes further. You can count how many microscopic degrees of freedom are there. If you have to store an energy delta E at a temperature T, then the number of microscopic degrees of freedom you need is given by this ratio. This connects microphysics with thermodynamics. So I have been saying that you can heat up space-time. So do we have a law like this for space-time? Can I sort of give an equipartition relation? It turns out you can. It turns out that if you take a region, three-dimensional normal region, and if there is certain amount of energy, more precisely the Komar energy in that region, that can be written as half kT times dA upon LP square. So the LP square is what I introduced into that heat density expression. It is something with the dimensions of area. So if you associate dA by LP square atoms or microscopic degrees of freedom with an area element dA, then this is just half n kT. Now this result you can prove, and let me try to do this in a somewhat picturesque manner. So this is real space, x, y, z at some constant t, and you look at an equipotential surface, which is a constant elapsed surface, and you associate with this surface a by LP square degrees of freedom. Now there is a normal, there is a gravitational force on there, and there are observers who are sitting there, and there are freely falling observers. Comparing these two, you can associate a local temperature, and from that local temperature, you can define an average temperature around this. So think of this like a microwave oven at this average temperature, and there is some matter inside. Suppose this matter has come into equipartition at this temperature. It might not have, but let us assume for a minute it has come into equipartition. If it has, then the number of bulk degrees of freedom I will associate here is the energy associated with that matter here, normal matter, divided by this half kT. What you can prove is that in all static geometries, Einstein's equation in that static geometry implies and is implied by this simple relation that this n surface should be equal to this n bulk. So I call this holographic equipartition. It is not used in the way string theorists, for example, talk about holography. This word is used in a more primitive sense of a surface to bulk correspondence. But there is yet another catch which one wants to unravel here. There has been lots of derivations of Einstein's equation from thermodynamic approach, and I'm unhappy with all of them. It is absolutely incongruous to claim that gravity is like a thermodynamic limit of some underlying system and then go and derive Einstein's equation. Einstein's equations are geometrical equations which provide relationship between geometrical variables and matter. If something is thermodynamic, you should be able to express the dynamics in terms of thermodynamic variables. So how do we do that? In order to do that, it turns out that the more convenient set of variables are this instead of metric, and this set instead of the Christoffel symbols. Then one can show that in all null surfaces, there is a direct correspondence between Q delta P and P delta Q with indices contracted in an appropriate manner with S delta T and T delta S. So what we thought are geometrical variables do have thermodynamic significance in null surfaces. What is more, I just described static spacetime, and static spacetimes are boring. We want to know how geometry is evolving. How geometry is evolving is given by this equation. If n surface is not equal to n bulk, you take that difference, and that difference drives, this is actually a Lie derivative with respect to time-like vector field. Something has gone wrong with the notation. So this object, it can be interpreted essentially as the heating or cooling of the spacetime that is driven by the deviation from the holographic equipartition. This single equation applied to all surfaces, this is like an integral form of the Gauss law, implies Einstein's equation, and Einstein's equation implies this. So the way you study dynamics is entirely in thermodynamic languages. Farewell to geometrical variables. This replaces the field equation for gravity. It is also interesting, and I want to spend a moment on that, to explain what happens to Newton's law of gravity here. I introduced so far three constants, h cross, c, and an area, LP square. I called it LP square. The temperature came out of h cross and c, and the entropy dependent on LP square. And the entropy chooses which theory of gravity you are choosing. If you look at the standard Newtonian force law, It will be m1, m2 upon r square in the Newtonian limit when you construct this theory, multiplied by this constant. Because of the structure of this, please resist your temptation to call this capital G and rewrite LP square as G h cross upon C cubed. That is wrong. What it tells you is that when h cross goes to 0, keeping other things constant, gravity just blows up in your face. Gravity is quantum mechanical at all scales. Exactly the way matter, which makes up this slight changer, is quantum mechanical at all scales. If I take h cross going to 0, every atom in this slight changer will collapse. When people do lattice dynamics and get elasticity as a limit, they're very careful. They will not put the h cross inside the atom to 0. They will put the h cross between the two atoms to 0, and that is how you take your classical limit. So at h cross going to 0, matter cannot exist. At h cross going to 0, space-time as we understand it cannot exist in this thing, which I find very, very satisfactory. OK, I think I will skip this because I have more important things to tell you. So let me just leave this. And it turns out that you can derive a host of things which has been known in the literature before, like the fluid mechanic description, equivalent fluid mechanic description of gravity, all at one go by introducing a very natural momentum for gravity, which this approach gives you. But I will not go into that. OK. Now let us ask the question. I started out with a guiding principle for dynamics. Then I said that in the macroscopic scales, if you identify it with the null normal to the null surfaces, then you can get all that we know about gravity. That part of the story is complete. But now we want to go in the other direction, go into the microscopic scale. Can we understand this from a deeper microscopic level? First of all, we want to know what is this null vector field which I have introduced as an auxiliary vector. What is its purpose? Where does it come from? Why are null vectors selected out? What is so special about null vectors? And also, how do we determine the heat density? I wrote it in terms of some P times del n, but it has an equivalent expression in this form, in dimensionless form, which is of this kind. Can I obtain this from microscopic consideration? Oh, OK. This is just an algebraic aside. OK. Essentially, what it tells you is that if you think of this NA like momentum, then this is the kind of term which you would expect rather than this del n square. So if the theory is internally consistent, there must be a way of writing this in terms of a quadratic in NA. It actually can be done, and what remains is an ignorable divergence term. OK? So what we are actually interested in is this expression. This is dimensionless. And can I get it out of something microscopic? The challenge here is that we don't know the full quantum theory of gravity. And yet I'm trying to obtain this object from some quantum gravitational consideration. Mathematically, we need to recognize discreteness of space-time. But at the same time, we are familiar with continuum mathematics. We are not very good at triangulating the space-time and working with that. How can I sort of reconcile these two? Actually, I don't have to. People have done it before. All of us have done it before. We have never been taught in that line. If you think of continuum fluid mechanics, there are two levels of description for it. One level is when you write down continuity equation and Euler's equation, and you define a velocity field at a particular point, density field at a point, etc., etc. Here, you completely ignore discreteness. You had to add things like temperature by hand from outside. And you don't introduce velocity dispersion at all. At a given point, there is a given velocity, which is the average velocity of the molecules. But we also know that the kinetic theory of gases works at one deeper level. There we use something called a distribution function, which actually counts. So this is a discrete process. It tells you the number of atoms or molecules in a small volume d3x in a momentum cell d3p. And if you read careful textbooks like Landau and Lifshitz fluid mechanics, he will tell you that this d3x is not mathematically infinitesimal, but it is practically infinitesimal. What it means is that it is infinitesimal enough for you to carry out calculus operations, but it is considered to be big enough to contain large number of atoms of the fluid, so that you can still talk in terms of average quantities. So this recognizes discreteness and also uses continuum mathematics. This is precisely what we want. And an atom at a point xi has an extra attribute, momentum. Because at a given point in the continuum fluid mechanics, the velocity is specified. But in kinetic theory, at a given point, there are a large number of atoms, and each atom can have its own momentum vector. And there is a dispersion around the momentum vector, which you can compute. And once the many atoms exist at a point in a loose sense of the word, you can calculate dispersions. So what we want to do is to translate this picture into atoms of space. It seems natural to think that the fundamental quantity in our theory, the heat density, should be proportional to the distribution function for the atoms of space at a point xi with some momentum labeled ni. So what I'm trying to find out is that this dimensionless object, this is the heating rate or whatever, which is proportional to some distribution function. This is what I want to find. So what would the distribution function be? I want to count how many atoms of space are there in this region. The most natural primitive idea would be it should either scale as the volume of that region or it should scale as the area of the bounding surface because of these holographic concepts which we have come up. So I want to associate with an event xi a volume or an area. This is a very weird notion. Normally, events or points in a space has 0 volume and 0 area. Okay? So I want to come up with a different structure in order to do that. This can be done using a concept called equigeodesic surfaces, which I will do next. In order to do that, I want to introduce to you, and even general relativists, or not everyone is familiar with the idea, that there is a completely equivalent formulation of classical general relativity without using metric, but using what is known as geodesic interval or Singer's world function. So geodesic interval essentially measures the distance between two events, okay, in a space-time. And given the distances between all points in space-time, it is equivalent to knowing the metric. So if you know the metric, you can compute this. And if you know this function, then by taking two gradients and taking appropriate limit, you can reconstruct this metric. So when you do this, this is the metric, and there are correction terms, etc., which are dependent on the acceleration. Now, there is a completely equivalent formulation. The 10 functions of space and time is traded off for one scalar function, only because it is a biscalar and not a genuine scalar. And you can redo everything which you want to do in classical differential geometry in terms of this. It's not very convenient, but in principle, it can be done. But in particular, it allows you to define what I call an equigeodesic surface. That's again a very elementary notion. It's just a sphere, so to speak. You start with a point, and you send out geodesics. This is simple flat space-time, and I have gone Euclidean now. And you go at the geodesic distance sigma, and you take the set of all points at equal geodesic distance. This is a equigeodesic surface. So in the simplest context, it will be like sigma square times the S3, which is going to sit on this in 4 dimensions. If you look at the area element or the volume element, both will scale as sigma cubed. If you do this, so both scales are sigma cubed. So if I try to associate a volume or area with this point by collapsing this equigeodesic surface to a point, both of them will vanish, which is exactly what you expect. What happens in a curved spacetime? Well, in curved spacetime, if you do exactly the same thing, you have a point, you can send out these geodesics, and you can define this. And this will pick up curvature correction. This root g and root h will have a term which is sigma square times this, which is exactly the term which we are after, but it is multiplied by sigma square. So again, when I collapse it to a point, it will vanish. Of course it should, because this is a formula known to Gauss, and this is classical geometry. In a classical geometry, points have 0 area and 0 volume. What happens is quantum gravity has to introduce, in some sense, this LP square into the picture. Now, we need a quantum of area for this idea to work, and this has to be a quantum gravitational effect. And I'm going to postulate, based on lots of investigations which has been done by many people, that one effect of quantum gravity would be to change the geodesic distance to some other function such that when sigma square goes to 0, there is a finite residue. Everything I'm going to tell hereafter is going to work for any arbitrary sigma square, arbitrary s of sigma square, but for simplicity, I will take this path. This is equivalent to saying that the quantum gravitational effects changes the metric to some dressed or renormalized metric, which is going to be a bitensor. And it is going to be singular in x going to x prime limit in order to make this work, for which you will have this as the length scale. If you do that, you can go ahead and work everything out. Now the number of atoms at a point x with an attribute, extra attribute ni, will scale as either volume or the area of a quantum Euclidean space in the limit of x bar going to x. So in the Euclidean space, when I go to the coincidence limit, I'm picking out the null surfaces, and because of which all the null vectors will come up and the origin will map to the Rindler horizon. So this solves part of the mystery. Then you go and just compute this. You compute the volume element with this correction term, and you go and compute the area element with this correction term, and then you find something very peculiar. When you take sigma going to 0 limit, in this expression, everything is scaled with this extra sigma here, so the volume elements go to 0. The volume associated with a point still remains 0, even after this correction is taken into account. But in the area case, when I take the sigma square going to 0, something survives. So points have 0 volume, but a finite area given by this expression. This is precisely what we want. This is also related to something which I don't have time to talk to. It tells you that space-time behaves as though it is two-dimensional at Planck scale. This is something which many people have arrived at from many different arguments. Here, there is a somewhat model-independent way of thinking about it. The rest is straightforward algebra. You can go and compute what this distribution function is. It will turn out to be exactly what we want, plus a 0-point contribution. This 0-point contribution is quite important. It essentially tells you that the number of degrees of freedom of a Planck two-sphere is 4 pi. That is 4 pi LP square divided by LP square. Why is this important? Because I told you long back that I have to give you the value of the cosmological constant, which is an arbitrary constant in this picture. So in order to do that, you have to understand the evolution of cosmology or the universe in this perspective. When you do that, the following picture emerges. Our universe can be described in terms of an inflationary phase and a late-time accelerating phase, and an in-between transition phase involving matter and radiation dominations. Its signature is in terms of 3 numbers, all of which having the dimensions of energy density. Inflationary phase is governed by one number, one pure number. There is another number which characterizes this phase, which is the energy density at the matter-radiation equality, and a third number, which is essentially the cosmological constant at this scale. In this approach, the n bulk will be equal to n surface at these 2 phases. It will be approximately equal if these are approximately d theta. And here, this will be grossly different, and that is what makes the universe evolve from one equipartition state to another equipartition state. Further, you find that when you work this through, there is a conserved quantity in these 3 phases which connects these 3 phases. In the conventional approach, these 3 numbers are completely independent. You can create an ensemble of universes by choosing any value you want for cosmological constant, inflation scales, and rho EQ. It's a 3-parameter family of universes. Here, these 3 are related. And if you don't take anything back from this lecture, just take this as a take-home message. This theory predicts that this rho inflation, rho equality, and rho lambda are connected by this formula. And if you plug in the values for rho inflation and rho equality, which probably will come from high energy physics, once the high energy physics have got their act together, they will tell us what the grand unified theory is and how that inflation took place. They will also tell you the dark matter density in the universe, and I can measure these 2, and then I can compute this value. Of course, today we are not in such a lucky position. Today, from cosmological observations, we know what this value is. We don't understand it, but we know its numerical value. We also know what this rho EQ is, again from cosmological observations. So given these 2, I can go back and calculate when inflation took place. Now, I could have got virtually any value I want out of this. I mean, in the sense that there is no way you could have guessed the value. It turns out to be between 1 and 7 times 10 to the 15 GeV. This is exactly the ballpark figure with grand unified theories are predicting. So this theory, and this is probably the only model putting together the principles of quantum theory and gravity, which makes a prediction, a testable prediction. This is a falsifiable theory. Tomorrow, if biceps comes and tells us that inflation did take place, but it took place outside this window, this theory is dead. So there is a prediction which says that if the cosmological constant has this value and rho equality has this value, then the inflation must have taken place around 10 to the 15 GeV. In fact, if you put the uncertainties here, it is very precise. It is within some 5% accuracy, it is something. But unfortunately, there is some reheating issues at the inflation, end of the inflation, which we don't have complete control on. We don't understand it very well. That increases the error bar to something like a factor of 5 or 7, but not more than that. It also tells you that there is some kind of a holistic approach which is demanded by this, which I want to now talk about, in the form of a bit of a speculation. What it tells you is that there is this energy momentum tensor for matter which can be sort of coupled to this Na and B. And you can give some probability distribution for the atoms of space, and you can calculate something like a partition function. Okay? If you do that, and you take for this probability whatever we have found, the exponential version of that, which is this RAB Na and B, then the field equation, the natural way of writing the field equations in this approach is like this. The expectation value that is averaging over this probability distribution, as well as any other quantum averaging of TAB, Na, and B should be equal to 1. So there is some average of TAB, maybe quantum average, and this Na and B should be averaged with this probability distribution, and this number should be 1. That tells you two things. First of all, it has some weird Machian flavor. If you put TAB equal to 0 everywhere, then you get 0 equals 1. That is a contradiction. So it sort of tells you that matter and geometry should emerge together. And the kind of freedom we had in doing cosmology in the standard general theory of relativity is taken away from you. This approach suggests that maybe we should not think of cosmology as part of general theory of relativity, and it should have an independent life of its own. Because general theory of relativity is a thermodynamic limit of a system. And thermodynamic limits require some time for thermalization. It is possible that the outer fringes of the universe are not in thermodynamic equilibrium the way we understand here, which means that there are corrections and the dynamics can be completely different, and you want to think of cosmology afresh. And what we have seen, this relation between three things which are unrelated in complete standard general relativity, is a first indication that this is a more holistic approach which you need. So there are some open questions which, for lack of time, I will not actually discuss. The main problem is matter. Actually, it is strange. Gravity is not the issue. So I have things like atoms of spacetime, distribution function for atoms of spacetime, etc., etc. I have absolutely no way of understanding matter. I have to put in matter by hand in terms of a stress tensor. This is exactly what Einstein did. He was never happy with it. And I don't think any one of us are happy with that. That needs to be sort of reconciled. And there is also this extremum of the action with the entropy extremum for gravity, but that is probably easier to understand in Euclidean thing. And there is some dynamical evolution for this distribution function. Further, the fact that null vectors emerge tells you that there are long correlations. I mean, we heard about it today morning in a different context, along the null surface. Spatially different point, but connected by a null ray can carry these correlations, which will, of course, have implications for things like Bell's theorem, etc., etc. But I haven't looked at any of these, but that is something for this community to think about. So just to summarize, if you demand that gravity should be immune to the 0 level of energy shift, it leads to a variational principle with an auxiliary null vector Ni. This variational principle, as well as the geometrical variables and the evolution equation for gravity. Let me repeat that it is completely meaningless to call gravity thermodynamic and in the end derive Einstein's equations. Einstein's equation of geometrical, they are not thermodynamic. This approach gives you thermodynamic meaning to geometrical variables. And if you take the number of atoms of space-time at an event to be proportional to the area measure of the equigeodesic surface, then you get the correct variational principle from it. Further, a Planck scale 2-sphere should have 4 pi degrees of freedom, which actually gives you a formula for the cosmological constant, which I believe this is the only approach which has given you a numerical value for the cosmological constant in terms of other parameters in the universe. Thank you very much.